Okay, so the main focus of these lectures are some applications of Hex bundles to other branches of mathematics, which happen through a particular locus inside of the modular space of Hex bundles, which is the Nilpotent cone. So in order to get to that, I will have to introduce the main object. So since Jacques will be speaking about the non-abelian Hodge correspondence and Hex bundles more in detail in his course, to avoid spoilers, I've decided to do today a more hands-on introduction, which will be based in the rank 1 case, which in spite of being simple, already contains a lot of the features that make the general theory so interesting. So these will be the plan for today. Tomorrow I'll move on to motivate through the application to Donagi-Pantev's program towards the proof of geometric Langlands through abelianization. And finally, I'll focus on some particular geometric features of the Nilpotent cone. Okay, so let me share my screen. I'm going to turn off my video because in any case, I don't have a connector with me. And this way, in any case, you won't see me. So can you confirm you can see my whiteboard?
Yes, we can.
And is it okay if I write this way? Or do you see it?
It's perpendicular to.
Okay, so no,
sideways.
it's not okay. Fine. So let me just, yeah, I wanted to use notes, but it's just not possible. Okay, so today we're gonna be introducing Hex bundles. Okay, so let's warm up with some examples. So Hex bundles have to do with modular spaces of bundles. Okay, so some examples of modular spaces of vector bundles. And I'll be focusing on curves. So these will be smooth, projective, connected, everything that's nice. Okay, so modular problems are classification problems in geometry. So typically one has a class of objects one wants to parameterize and intends to do so in such a way that the parameterizing space captures how these objects vary in families. So in particular, one can consider vector bundles on a given curve. Say, let's start by the very first example, which is the Riemann surface. And try and see their isomorphism classes. Right, so we know that line bundles, so the Picard variety of P1 is just Z, right? Because any line bundle is just given by the divisor that consists of a point multiplied by an integer. Okay, now also there's a beautiful theorem, so it's called the Birkhoff-Grothendieck theorem. That says that any line bundle, any vector bundle on P1, so holomorphic vector bundle. Sorry about the board, but this whiteboard is not very, yeah, it doesn't allow a lot of options. So any such bundle is going to be isomorphic to a direct sum of line bundles. So it will be given by an integers where n is the rank of E. Okay, right, so from the point of view of classification, P1 is not very interesting when it comes to bundles. Let's see what happens in genus 1. So in genus 1, we have a donut. Let's take an elliptic cursor with a mark point. So in this case, the Jacobian is a bit more interesting. So the Abel-Jacobi map, which sends a point of the curve to the divisor given by, say, x minus the base point, is an isomorphism in this case. So another way to do it, which already puts up some tools, is as follows. The Jacobian can be expressed as a quotient. It's an abelian variety. It's the vector space given by the 0, 1 forms on X, anti-holomorphic differentials by the lattice given by the first homology. Also, X is just C quotiented by a lattice, which can be identified with the first homotopy group with base point at x0. And let me recall that the lattice here is embedded. I hope this is not too slow. I'm also thinking of students, so please do tell me if you get very bored and I can just go a bit more quickly. So by serduality, we identify anti-holomorphic forms with a dual of holomorphic forms. And just if one has a cycle, okay, thanks, Aswin. I think so too. I mean, I think slow is always good, but depends also on the expertise of the audience. All right, so the embedding of the lattice into the anti-holomorphic forms is just given by the pairing that's given by integration along the cycle. Okay, so now, then the Abel-Jacobi map can easily be seen to be an isomorphism by writing it in a slightly different way. So to each point, one assigns the integral over any path from the base point to x. This is easily seen to be independent of the path precisely because on x we're quotienting by the lattice of loop space at x0. And it's also easily seen to be an isomorphism, which essentially follows from the perfection, you say, I don't know, of the pairing given by integral on singular homology. Okay, so a bit more interesting, but still known objects. Let's see on genus at least 2. So we have a torus with at least 2 holes. And let me analyze this isomorphism, which will allow to put the gauge techniques into place. Okay, so here we're classifying topologically trivial line bundles on X, right? So what we want to see is how many ways to endow them. So to endow these topologically trivial, which is unique. So we don't want to classify topologically trivial, classify holomorphic structures. So there is just one topologically trivial line bundle of degree 0. This is given by the degree. So we want to classify all the possible holomorphic structures it can be endowed with. So an application of the Nylander-Nirenberg theorem allows to identify holomorphic structures with delta bar operators. So call L the line bundle. So we will be considering sections of L into 0, 1, sections. This is a delta bar operator. So the delta bar operator satisfies that it's integrable, but this is trivial on curves, right? Because these are Keller, and so there's no forms of type 0, 2. And it should satisfy the Leibniz rule. So given any section and a function, so this is a function on the curve, and this is a section of the bundle. It should satisfy delta bar f times s plus f delta bar L of s. Okay, right, so these are the objects to be classified. Now we need an isomorphism notion. Okay, so an isomorphism is going to be given by an endomorphism of the line bundle, an automorphism of the line bundle, right? So this is just given by, this notation may be not super good. Let's call it S. So S is going to be a map from the curve to C star simply, right? And it should exchange. So if we consider delta 1 bar on L and delta 2 bar to delta bar operators, well, this automorphism should exchange them, namely delta 1 composed with S should be delta 2. So S composed with delta 2, okay? Okay, so now if we write what this means, we find that, well, this is, maybe I'll keep writing here for a minute. Okay, this, where did it go? Okay, I seem to have deleted it, okay. Right, so if we write what this means, this is just, so this is true if and only for every holomorphic framing. For holomorphic for delta 1, of course, so that S delta 1 of x equals 0. What happens is that delta 2 of S applied to E is also 0. Okay, but writing this is just, I mean, writing this, we get the following equation. Just developing, we find that delta bar F times S plus F delta bar of S plus F, delta bar 2 of S equals 0. And this is again equivalent to F minus 1 delta bar of F plus delta 2 applied to S equals 0. Okay, so now suppose I've changed notations. F is S. Sorry, my notes don't match the board. So F is S and S is C. So here I have S and here I have C. Okay, now it's correct. Okay, fine. Well, suppose now that S belongs to the connected component of the gauge group. So the gauge group are just the maps from X to C star. This is the complex gauge group. And its connected component is just given by the exponential of maps from X to C. Well, in this case, we are seeing here that this isomorphism notion is just acting by the connected component by translating by a boundary. Namely, so delta bar operators is an affine space modeled on the 0-1 forms. So in here, we're translating our given delta bar operator by, so delta of the logarithm of S, which is well defined if we are in the connected component. Okay, so in this way, we have the delta bar operators quotiented by G0 is just the 0-1 homology. Okay. Right, so we have the first part. Now we see that up to quotient by isomorphism, we find anti-holomorphic structures. What happens with the lattice? Well, if we embed the connected component of the gauge group inside of the whole thing, we find that the group of connected components is identified with H1 of X, Z. And the way this works is the following. So we have a map from X to C star, and this induces a map from the fundamental group of the surface into Z. So its class here and induces an isomorphism between the homology and the group of connected components. Okay, so as such, we find that the Jacobian is indeed the quotient, right, claimed. Okay, are there questions so far? Okay.
I don't see any in the chat, but if anybody would like to ask a question, you can type it out, or yeah, just let me know through the chat. Yeah, maybe Anna, you can go ahead for now, okay. And if I see any questions at your next pause, I'll ask.
Okay. Fine. So, okay, we have some examples in mind, some vector bundle examples. Let's move on to Hex bundles. In rank 1 for now. So, definition, a Hex bundle of rank 1 on degree 0 thing is a point of the cotangent bundle of the Jacobian. Okay. Let's call this somehow, this will, so I will call MX10. This will be this will denote the modular space of Hex bundles of rank 1 and degree 0. Okay. All right, but this is very simple. This is just the trivial bundle with fiber. H0x of k. Okay, I see someone asks why it can be written as a logarithm. I'm assuming it is, in fact. Let's see. So G0 is defined by the exact sequence. Let's see. I'm going to identify G0 with
omega 0 x c. Right, and the way it's embedded is via the exponential. So when I'm taking the logarithm, just by definition, I'm taking an element in here, right? So just by the way it's constructed, it's the logarithm of the logarithm is well defined. So where am I? Okay. So in this case, so the modulus piece is very simple. It's just a trivial bundle over the Jacobian with fiber, the holomorphic differentials. So the way to see this is by Serre duality. So the tangent space at a given line bundle on the Jacobian. So by what we saw before is just the vector space. So that given by the universal cover. So if one dualizes to get the cotangent, this is just 810, which is precisely holomorphic forms. So as Aswin was pointing out, a Higgs bundle is it's a vector bundle together with some extra structure. And this extra structure is called a Higgs field. Okay, now it turns out that the modular space of Higgs bundles has a very rich geometry. First of all, we find it is a holomorphic symplectic manifold. I mean, this is not very mysterious. It's a cotangent bundle, so one can take the canonical form and its derivative gives a symplectic form that's holomorphic. So it's, first of all, it has a complex structure inherent from that of the Jacobian. It's called, let's call it I, and it's also it has a holomorphically symplectic differential form, sorry. So this is just given by, again, the duality, the pairing given by Serre duality, right? So if one takes, so this is a variation of the holomorphic structure. So it's a 0-1 form. This is a variation of the Higgs field. So it's a 1-0 form. And likewise, so this can just be defined by Serre duality. And in fact, it matches the differential of the Liouville form. Okay. But there's another complex structure, which comes from the realization of this modular space as the modular space of flat connections. So the modular space is isomorphic, not as a complex manifold, but as a real manifold to the modular space of flat connections. So how does one see that? Well, I mean, we have Hodge theory that tells us that there is an isomorphism between the first cohomology with complex coefficients and the direct sum of 1, 0 and 0, 1 forms. And moreover, one can always find a harmonic representative so lambda L for an operator is L adjoint plus L adjoint L. Here I'm assuming I've chosen a metric for now, let's say the Keller metric on the manifold, on the curve. But it could be a metric on the bundle. It will be in a second. And here as well, we can choose harmonic representatives. Harmonic for the delta operator. Okay. So starting from a Hex bundle, say a delta bar operator, which will be given by delta bar plus some 0, 1 form and a Higgs field, we want to build a flat connection. And how does one do that? Well, take the Chern connection, first of all, for some Hermitian metric. So on the line bundle we were starting with. So there is a unique Chern connection. I mean, it's a connection that's compatible with the metric and that has 0, 1 part equals to the delta bar operator. That's the definition of the Chern connection. And add to it the Higgs field plus its adjoint for the given metric. Okay. So the result is that there exists a unique up to gauge transformations so a unique metric such that the given connection is flat. Okay. So the proof is very easy in this case, because up to gauge, one can assume that the form is harmonic. So we have some harmonic plus equivandary. So this is some function. And so the metric can be taken to be the exponential of twice the real part of f. So one can check that in this case, the metric one gets is flat, and not only that, but the metric is harmonic for the connection. Okay, so this yields an isomorphism between the modular space of bundle or Hex bundles and the modular space of flat connections. So a flat connection is given by a homomorphism from the fundamental group of the surface to C star. And these consist of 2G copies of C star, right? So one sees very simply a complex structure emerge, which is just coming from the C star, from the complex structure of C star, just multiplication by I on C star. Okay, and in fact, this is the complex structure of a Keller structure whose symplectic form is given by cup product. So on H1C times H1C, one takes V, so U and V, which are morphisms from pi1 to C, are mapped to the following. Choosing a basis of the fundamental group, one can just take UAI. So AI, BI are a basis of a fundamental group. So they satisfy the relation written there. And so one evaluates when one evaluates U and V on AI and BI in this form. So Goldman proved this is a symplectic form. Okay, right. So this story generalizes with some modifications. I mean, a lot of non-trivial modifications, in fact, to higher rank. So let me briefly explain the higher rank case. To then be able to move on to the main subject of the talk. Okay, so we will be considering moduli spaces, so classifying spaces. There will be two main kinds of moduli space. So the moduli space of vector bundles, of rank n, so n is the rank and d is the degree. So this has as close points vector bundles of rank n and degree d, but not all of them are suited for classification. So one needs to consider semi-stable guys. So if they can be stable, they could be semi-stable. And the relation is up to S equivalence, which in fact in the stable case is isomorphism. So you can think of isomorphisms, isomorphism classes of bundles. At least generically, this will be true. So what is semi-stability? Let me put it here. So a bundle is semi-stable if for every subbundle, which is non-trivial, so it cannot be the total and it cannot be zero, the slope, so subbundle, the slope of f, which is defined to be the degree of f mod its rank, is strictly smaller for stable, could be equal for semi-stable to the slope of E. Okay, so first remark is that all line bundles are stable. right? Because there's no non-trivial subbundle. And therefore the Jacobian is precisely the modular space of line bundles. This is, we all knew. Another remark is that in the case of genus 0, we've already seen that the moduli space is a point when we fix the invariant, so it's not very interesting. So yeah, why is it a point? Maybe I should comment a little bit on that. So NP1 of ND equals a point, right? Why is that? Well, because of the semi-stability, a priori one could have direct sums of line bundles of different degrees, but this wouldn't be semi-stable. So it will be semi-stable only when all degrees are the same. Okay, so the modular space is certainly not very interesting. And for the donut, it's a bit better. So this was studied by Atillo originally. And what we have is that the modular space is the symmetric product of the higher common divisor of between the rank and the degree of the curve. So nicer, but still not very, not super interesting. So things start getting more exciting from genus 2 onwards. Okay, let me delete this because I want to complete in here. So now I'm going to consider as well the modular space of Hex bundles. So this is the modular space of Hex bundles. Which equals, so its close points are pairs of, again, semi-stable, I'll define in a minute, pairs given by a vector bundle and a Higgs field. So in the case of rank 1, this was just a holomorphic one form. But here it's a holomorphic section of the endomorphism bundle of E, tensored by the canonical. Right? So in the case of a line bundle, this is just a trivial bundle. This is why we only get holomorphic one forms. And again, we quotient by S equivalence. Right, so in the case of a Hex bundle, semi-stability is defined very similarly, but instead of taking all subbundles, we only consider those subbundles that are fixed by sorry, that are left invariant by the Higgs field. Okay, so a remark is that if E is semi-stable as a vector bundle, then with any Higgs field, it will still be semi-stable as a Higgs bundle. But it's not true that any semi-stable Higgs bundle has underlying semi-stable bundle. I'll give an example in a minute. Let me go back to the examples. Okay, I need to change whiteboards. I've just saved this, and I need to close the document and open a new one. So maybe we can take advantage while I do that for some more questions.
So there's a question from Duong Din. They ask, do we need to pay attention to the relative parity of N and D?
Oh, yeah, certainly. I mean, things change a lot. Well, it depends for what, but yeah. And so the modular space will not be smooth for N and D not coprime. He said parity, or what did he say?
Yeah, the question.
Well, it's a matter.
Yeah, go ahead, please.
Yeah, so it's a matter of being or not coprime. So right, except for genus 2, where actually it's always smooth, which is a bit of a surprise. It came up as a bit of a surprise. In all of the cases, it will have singularities. So yeah, one has to be careful. Maybe what he means by parity is whether the degree is even or odd. So for degree even, so the isomorphism type of the modular space only depends on the parity of the degree. So again, yes, if the degree is 0, then, well, if the degree 0 and n is, if the degree 0, there will be singularities. If degree is 1, then no. So one can reduce that to this case, degree 0 or 1, coprime or not coprime. I hope this answers the question.
Yeah, thank you. I think.
How much of the Hodge, non-abelian Hodge package extends to the stack? Well, yeah, that's a good question. So the problem with the stack, I mean, it doesn't. It doesn't, but still one can do quite a lot of things. Maybe we can talk about this in another moment, because it's not going to be meaningful right now for them, for the course, and I'm running a bit late.
Yeah, we can take questions also in the Q&A session at the end. So
okay,
if that works better for you.
Yep. Well, no, I mean, basic questions I can maybe, but this requires a bit more. Exactly. Yeah. Development.
Right. So longer discussions we can postpone to the end. Yeah.
Okay. So someone asked what modular space means. Okay, I haven't defined what a modular space means. So normally one has a classification problem. So in this case, we want to see if the functor, say, that assigns to a scheme isomorphism classes of vector bundles over that scheme times the curve has a representative. So in general, this is not true, and that's why one needs stacks. But one can have there's a less refined notion. Sorry, not less refined. There is a notion of a coarse modular space. So this would co-represent the factor. This exists in more cases. So for us, since this is a 3-hour course, a modular space will just mean certain objects up to an equivalence relation. But there's a lot more to it, yes. Okay. Okay. So I was going back to the examples. So I have what, 20 minutes, Aswin? We started a bit late.
Yeah, but 20 minutes should be.
Yeah. Okay. Okay, so back to the examples. So for genus 1, it's for genus 0. For genus 0, what are Hex bundles? Anyone knows? Anyone wants to try? Well, it's empty. Because in spite of the modular space being a point, there are no Hex bundles precisely because what would a Hex bundle be? So we have that E is a direct sum, semi-stable. It's a direct sum of ODIs, and here the S equivalence notion is important. is very important, because a priori one can have some upper diagonal Higgs field, so zeros over the diagonal, but there could be something happening provided that the degrees are sufficiently or are ordered in the right way. But S equivalence will kill this, and this is because of the shape of the bundle. So I leave this maybe yeah, I haven't defined S equivalence. So just bear in mind that S equivalence is a delicate issue and can produce things like that. So genus equals 1, then the moduli space is again a symmetric product, in this case, of the cotangent bundle of the curve. And again, the power will be the highest common divisor between n and d. So for the person who asked whether the relative parity matters, yes, certainly. So we will get different moduli spaces for different relative parity. Right. Okay, so we saw some very interesting features in the case of rank 1. So for example, we had a cotangent space. This is not true anymore, but the modular space of Higgs bundles partially compactifies the cotangent bundle of the stable locus. Sorry. So there's an open dense subset that's given by a cotangent space. And not only that, but the holomorphic differential extends to the stable locus of the moduli space. And here it's worth noticing that the smooth locus contains more points than just the cotangent bundle. So an example is the following. So take the canonical bundle 1/2, and one can produce a Higgs bundle just by using the identity. So let me check that this is correct. So K3 K1. So one just maps the K1/2 to itself by the identity. This is what I mean here, okay, with this arrow. So clearly the underlying bundle is unstable. So it's not this Higgs bundle is not it's not a point on the cotangent of the stable locus of the moduli space. And this also illustrates this example also illustrates that the locus given by points of the moduli space of Higgs bundles, and this will be meaningful in the sequel, with unstable underlying bundle is non-empty. Okay, so this is a difference with the moduli space of rank 1 Higgs bundles. So I've mentioned the symplectic form omega I, and in fact, just let me say that it has the same shape. So it's against their duality. One can prove that the tangent space to the moduli space of bundles is given by I0 of H1 of the endomorphisms of E, so that on the cotangent bundle there's their duality, and in fact it can be seen to extend to the stable locus. of the modular space of Hex bundles. So on T, so dualities are yields. Okay. And similarly, there's the non-abelian Hodge theorem. Which establishes a real analytic isomorphism between the modular space of Hex bundles and the modular space of flat connections. So again, flat connections are given by representations of the fundamental group now into the group GL and C, up to conjugation by GL and C. But not all homomorphisms are possible. In this case, one is to take reductive homomorphisms. Okay. Right, so this is a very important theorem. I think Jacques will talk more about that. And one of the first applications was the realization through this isomorphism that so I in omega is complex structure I. Yeah, it's complex structure I. Yes. So complex structure I is the complex structure that's natural in the modular space of Hex bundles. Complex structure J is the structure that's natural in the flat connection modular space or Betty modular space, which analytically are the same. And this is induced by the structure of the group, because by choosing a basis of the fundamental group, then one can express this as a quotient inside 2G copies of the group. Okay. Right. So one of the first applications of the non-abelian Hodge theorem is to realize that modular spaces of certain Hex bundles, so paired, are mirrors. So let's move on to mirror symmetry. So mirror symmetry has different mathematical approaches. There's a lot of work towards unification or analysis of how and which are equivalent and to which extent. But for us, we will say that a pair of Calabi-Yau manifolds are mirrors if there exist vibrations over a common base such that the fibers are special Lagrangian dual tori. Okay, so for example, in the case of the modular space of rank 1 Hex bundles, so this is a very trivial example because just the second projection to the holomorphic differentials is a vibration by tori. Okay, they are actually easily seen to be Lagrangian, so complex Lagrangian for I. So since, and this I forgot to mention before, IJ and K, which is just the composition, they underlie a hyperkähler structure. such that omega I is the symplectic form for the Kähler structure associated to J, and omega, and the imaginary part is the symplectic form associated to the Kähler structure for K. So then up to a hyperkähler rotation, one has that the fibers are special Lagrangian for J and K. Okay, so in this way, we have that the modular space of rank 1 Hex bundles is its own mirror. So by the way, this is what's usually called SYZ mirror symmetry. Where is it? Okay, this thing does weird things. I've lost what I've written. Okay, so SYZ, Strominger, Yau, and Zaslow. All right, what happens in higher rank? So in higher rank, we have also complex Lagrangian fibrations, which are map. So there's a map from the modular space of Higgs bundles to a vector space, which is given by sections of successive powers of the canonical bundle. So here, given a Higgs bundle, one just takes the characteristic polynomial of the Higgs field. So this is a priori something formal, but the coefficients are well defined. They're just given by evaluating invariant, conjugacy invariant polynomials on the Higgs field, and therefore they define sections of powers of the canonical bundle. Okay, so this is the Hitchin map or Hitchin system, and this is the Hitchin base. It's called the Hitchin system because it's a completely integrable Hamiltonian system. So in this case, the generic fibers are also Jacobians, but not of X, of course, but of some cover of X. So for a generic point. And the spectral curve, Jacques will say more about that, but this is a ramified N-to-1 cover, which over a point parameterizes the eigenvalues. So an order in this case. There's also the Cameral cover, which would parameterize order eigenvalues. So eigenvalues of phi of X for phi, so E phi in the pre-image of B. Okay, so the first remark is that this does not depend on phi, although I have to specify to explain what these eigenvalues correspond to. It just depends on the point on the base, okay? And also another remark is that it will be ramified, because already in rank 1, for example, we have that the Higgs field is just a section of the canonical bundle, and this will always vanish at some point. What this translates into for higher rank is that the Higgs field cannot be semi-simple at every point, and it will have some nilpotent part somewhere, and therefore there will be multiple zero eigenvalues. Okay, I'm running out of time. So let me just finish by saying that, so therefore, the modular space is also self-dual. Self-dual, this is not the word, it's also its own mirror partner. Okay, so there's more things going on here. Let me just briefly mention that Hex bundles can be defined for other reductively groups. G Hex bundles. And in this case, the mirror will be given by Hex bundles associated to the dual Langlands group. So we also have a notion of a Hitchin map, which can easily be defined through the Chevalier morphism. So the Chevalier morphism goes from the Lie algebra to GRT quotient, which can be realized as a quotient of the torus that divide. Okay, so let me stop here. Thank you for.
Thank you, Anna, for a wonderful talk. Let's all thank Anna. We can use Zoom has these virtual ways to applaud. So, and now we can take some questions as well. So maybe I'll begin with. So I don't know if they're still here actually in the room. I'm not sure. I think they may have left the room. So maybe we can then move to Aswin's question. Aswin, would you like to ask your question about stacks?
Oh, I think Anna wanted to postpone. I wasn't sure if she meant for.
No, I mean, well, I can say something. So yes, I know it doesn't. I can't be very. I mean, I'm not sure of the details, but the main problem is that the stack has a complex as a cotangent bundle, and these prevents from the non-abelian Hodge to translate to the stack in these terms. But having said that, there are several things that can be done. So yeah, I don't have a very good answer for that, but I would be interested also in understanding this better. So this could be a discussion subject. So if someone in the audience is an expert in this, that'd be nice to hear.
I mean, if I could just add, so the usual way in which people discuss like the 3 columns of non-abelian Hodge, the Hex bundles, the flat connections, and the petty character variety, it seems like there are stacky analogs of all of them. I just don't know if the analog of solving a PDE, what's the analog of that in the stacky world? That's the thing. I don't know.
There is some physics interpretation. Aswin, you had something about the physics interpretation of the stacky thing. You once told me some comment about this. Maybe that will be in the spirit of this conference.
In some cases, okay. So in the general case, I think we will see this more in Jacques Houtebi's course. So performing this non-abelian Hodge amounts to solving some PDE called Hitchin's PDE, and you could ask if you relax some conditions there, like instead of your, say, vector bundle, principal bundle being irreducible, maybe the structure group is reduced and so on. Is there some extension of that story there? I mean, there are some simple examples where there's some physics argument why that should extend, but I don't know a general theory.
Yeah, I cannot answer
to that either.
So if anyone has questions, please raise your hand or type it in the chat box. But you can raise your hand now and I can unmute you so that you can ask the question verbally.
I've seen someone ask whether I can give some references. There are plenty in the abstract. Probably, I'm not sure if I put it, but there's a great paper by Goldman and Xia, which is Hex Bundles in rank 1, something like that. And that's on the archive. So the language they use is a bit more advanced than what I've done, but one can extract very basic stuff from there. Also, a nice reference is the book by Wells, Differential Analysis on Non-Complex Manifolds, and in particular an appendix to the 3rd edition there by Oscar Garcia Prada that gives a very nice overview of these non-abelian Hodge correspondence and several things about Hex bundles.
Any other questions? So there was a question from one person who seems to have left. Maybe I can just ask the question anyway. It will be recorded. So I think you may have answered this question during the talk, but let me ask it again. So on the stable locus, the question reads, on the stable locus in the non-coprime case, there should be a symplectic form, which I think you then described after this question was asked. Will it extend everywhere?
Well, it doesn't, I mean, it doesn't make sense over the singularities. It does extend to the smooth locus, to all the smooth locus, but not to the singularities. I mean, there are automorphisms operating. So when one talks about the Hex bundle being holomorphically symplectic, one refers that the smooth part is has a holomorphic symplectic structure.
So I guess if you want to include the singularities, you have to work with this with some derived
You would, yeah.
To get the symplectic structure. Any other questions? Since we're sort of running on a slightly tighter schedule than normal today because the introduction has pushed everything back a little bit. So since we have only 10 minutes, maybe we can postpone other discussion to the next talk or to the Slack channel. Let's thank Anna again for a wonderful talk.